Logarithms. Everyday logarithms. So one of the examples that we see a lot is earthquakes. So earthquakes have a scale that's designed so an increase in 1 unit represents a 10-fold increase in the power of the earthquake. So to go from 2 to 3, that's a whole 10-fold difference. So it's 10 times greater to have an earthquake that's 3 rather than the 2. So that can do a lot more destruction, right, if you go up in the scale. Now, chemistry is also another one. So we use pH to measure the molar concentration of the hydrogen ions. Now, molar concentration really just means it's moles. So how much stuff per liter? That's all that means there. It also could be represented as a big M. So sometimes you'll see it as moles per liter or molarity, which stands for moles per liter. Now, we have a scale of pH. This is kind of interesting, right? If we go, right, it's a scale from 1 to 14. Now, somewhere in the middle, right, there's 7. And that's actually our neutral zone. Then anything so if we go to the left from 7, we become more acidic, right? So you're the most acidic when you're 1, right? This is the most acidic. But if you want to go to basic, you want to increase to the right from 7, like right where it's neutral. So more basic as we move to the right. Right, and so then 14 would be the most basic. So pH, right, as we move to the left, we're becoming more acidic. Or if we move to the right, we're becoming more basic. So it's a little bit different than a usual scale because it's measuring 2 different things. Now, a calculation to find the pH, right? This is really important. How do we find pH? Well, pH, all we have to do is take the negative log of the concentration of the hydrogen ions, which will be in the moles per liter, right? So we'll see it like that. So we do close brackets to show it's the concentration of the hydrogen ions, which is just this right here. Now, what happens if we want to find, say, the concentration? Like how much moles per liter is there in a solution, right? So what we're actually going to do, right, to undo this, to solve for this, right, it's just the hydrogen ion concentration, which is equal to 10 times this negative pH. So to undo this, we get this, right? And if you're not quite sure, you can always look this up, or you can look back at other examples to kind of go back to how we would solve for that. Now let's go over some examples. Example 1, a 5.4 earthquake hits Southern California. A few weeks later, a 3.4 earthquake hits Northern California. What's the difference in magnitude between these 2 earthquakes? So we have a 5.4 earthquake, and then we have a 3.4 earthquake. So we're asking what's the difference in magnitude between these. So it's just kind of to think through what that really would be, right? So we have 3.4. Well, somewhere in between would be with a 4.4. And then we get to 5.4, right? And so to go from 3.4 to 4.4, it's a whole 10-fold increase, right? And to go from 4.4 to 5.4, it's another 10-fold. So in order to get the whole difference, you would actually need to multiply these 2 together. So to go from 3.4 to 5.4, you go 10 times 10, which is equal to 100. So there's 100, right? This is 100 times greater in magnitude. There's 100 difference in magnitude between the 2. So therefore, the 5.4 is going to do a lot more damage. So you can kind of see why when you see 3.4 to 5.4, it's only 2, right? It's not, doesn't seem like that big of a difference, but it's really going to be a lot bigger of a difference because it's a 100-fold difference. Example 2, lemon juice has a pH of 2.2. Find the concentration of H+. So we're going to actually use our second equation. So what does our second equation look like? Well, right, we have the H+, which is what we're trying to solve for, which is equal to 10 raised to the negative pH, right? So this means that this goes here, right? And that's all we have to do is plug that in. So we find H plus by 10 to the negative 2.2. Let's get our calculators out. So we go 10. We're going to do this x to the y to do the exponent. And then we're going to actually close brackets this negative 2.2, close brackets. Notice it goes 0 minus 2.2. Right, that would be the same thing as just going negative 2.2. For some reason, the calculator needs to do it that way, but it still is the same thing. And we get 0.00631. And what's our, right, so this is the concentration, right? So, right, this is molarity or moles per liter. So moles per liter. Right, so it's just amount of stuff in a certain amount of volume. Example 3. A soda has a hydrogen concentration of 3.16 times 10 to the negative 3 moles per liter. What's the pH? So we're going to be using the second equation, where we do pH equals to the negative log, right, of H plus. So this is going to be our H plus. That's what that is, right? So concentration. So I'm going to plug this in. I'm going to get negative log, right, and we're just going to plug that in. So let's get a calculator out, but I'm going to show you something. So I like this calculator. So this is desmos.com/scientific. So this is kind of easier than say the calculator that's given just on the free computer. So let's try this. So I'm going to go to functions. Or first I'm actually going to go negative. Then I'm going to go to the functions and I see a log. And then I'm going to type, go back, I'm going to go 3.16 times 10 to the negative 3. So 16. So let's actually see. This is why I love this, because you can kind of show. It's easier to fix your mistakes. Now I need to go negative 3, and we get 2.5, and we'll just leave it like that. So that would be our pH. So what's our pH? pH is equal to 2.5. Now, would we say that's acidic? Well, it's closer to 1, so we would definitely say that's pretty acidic. So this would be our solution.